All right, line W1, learning task 9, connect VFDs. This is an important learning task to cover. When I was going through apprenticeship schooling, VFDs were still very new. And as a result, we didn't know a lot about them. We made a lot of mistakes out in the field when we were connecting them, had a lot of issues that we had to go and track down. This learning task here is actually relatively new, and it is going to go and give you a lot of good information. I've read through this a couple of times. This one is going to go and just kind of help guide your installation. It's not going to be prescriptive, but it's going to give you something that you should, kind of keep underneath, under observation anytime that you are connecting these inside the field, particularly just the recommendations on cabling type and filtering and things like that. We're going to talk about the components that we are going to go and have inside of here. Now, our VFDs are going to go and have controls that are going to be, part of what they are going to go and deal with. But there's going to be more to the system than just the VFD itself. We are going to go and have the VFD, which is going to be all of this that we're going to see inside here. We're going to go and have the motor, and then in between the motors and our drive, on the incoming side of our drive and on the outgoing of our side, we should have some sort of a power conditioning equipment. This is going to be equipment that's going to allow us to go and filter, take out a lot of the garbage that we would see otherwise on our induced waveforms coming from these. We are also going to have to look last of all at what our operator interface is going to be, how our operators are going to be able to turn this thing on, speed it up, slow it down, etc. Let's talk about the center part of this box here first, the VFD. What we're seeing inside of here is we are seeing a VSI type of variable frequency drive. The VSI is also commonly going to be used as our PWM types. If we go and take a look at them, we see that there's three main components where we convert our AC into our DC, where we filter or smooth our DC, we call that the DC link, and then where we are going to go and chop up the DC and form synthetic AC. We're going to call that section the inverter. This one is a fairly holistic drawing covering a whole pile of components all at the same time. It does have some new components inside of here. Primarily, you're seeing the GTO SCRs, the gate turn on, gate turn off SCRs, where we're able to go and shut these things off, so I can kill all power coming into here, so that I can discharge everything, same as I can go and kill any of these SCRs over here without having to wait for any of my holding current to drop through. We're also seeing that we've got a lot more filtering on our outputs that has been activated over here, where I'm going to have small capacitors inside of there that are going to go and charge up and then discharge back into my motor circuit itself. And then this section over here is just going to be my flyback diodes that are going to allow me to go and regenerate back into that circuit, right? Anytime that we are not driving our motor windings, then our motor windings are going to be collapsing, sending voltage back in it. So they would send it back in through those, and all of that voltage would then end up back on my DC bus. We'd use it to charge that cap there once again. As far as the technologies that are going to be in play, what we covered in the previous learning task is correct. The VVI is more or less gone. We are going to mostly see VSI or PWM types, or the CSI, the current source inverter types. With our VSI that we're showing over here, we are going to go and have a cap in the very center of this thing that is going to go and charge up. And it's going to go and charge up, and it's going to go put out a amount of current that is going to go and smooth whatever our waveform is going to go and look like. If we take a look at the actual switching, we see that we're going to be switching full line-to-line values of voltage, but that line-to-line value of voltage, as it switches, then we are going to go and have currents. That is electrons that are going to leave from this charged up capacitor that are going to try to find their way back through the motor all the way back to the other plate of the capacitor. And so we get the smoothing action of the current. It looks something like this. Up in the top there, we see that we have got our PWM waveforms themselves, where we see that we've got DC that's being applied in short little bursts. Okay, a little burst of DC, another little burst of DC. This is going to be a two-stage DC that we're seeing off of this one, where we have got two separate ones, and we can add those two together to get higher ones, and overall it gives us the same sort of effect as having a sine wave. What's really cool about it is the fact that we've got this cap in here. And so every time that the DC, as the DC itself is starting to go and build like this, switch over, every time that the DC shuts off, the cap carries through until the next DC pulse picks it up, and then carries through until the next DC pulse picks it up. If you were to go and zoom in on this line, you would see that this line isn't really a straight set of lines, but rather it's going to be small curves onto each of those that are just going to be part of that universal curve that we've seen back in second year when we were looking at the discharge of capacitors. For our VSI, we're going to go and use that cap to filter the voltage waveform. For the CSI, we're going to go and use the inductor that is going to go and filter out our current. Once again, it's going to be whatever's on the incoming side that is going to go and filter what's coming from, what's being charged up inside of here, my VSI. Over here is going to go and use this inductor. And then I've got my cap on the downstream side. The CSI is just going to go in reverse, the way that those two are placed in there. Not super critical for what we are going to look at because we're not building these in the field. We're just going to be utilizing these ones. Of the two, there is going to be more common that we are going to go and run to the VSI. VSI are just more efficient. Higher power factor, lower harmonic distortion. We don't see the same sort of flyback into the rest of our circuits. We can also go and use VSIs to go and create, because we're going to be charging up that cap, we can create three-phase supply from a single-phase system. Our CSIs are usually incapable of this. That we can't do that because our CSIs are going to be storing their energy inside of an inductor field rather than inside of a capacitor. If we got it inside of a capacitor, we can charge that capacitor on single-phase AC and then create our single-phase AC and then create synthetic three-phase AC back out of them. We do want to be careful about when we apply these things that we're going to go and filter. Power conditioning equipment, or PCE, as you are sometimes going to hear this referred to, or filtering. It's all of this is going to be the same thing. We're going to try to address this thing that is going to be called our THD, or total harmonic distortion. We're going to cover this inside of C4, which is going to be our line that's going to be dealing with power quality. But THD is total harmonic distortion. Total harmonic distortion is just going to be a measure of the amount of harmonics that exist on your system. Every system has them, just some are worse than others. What we want to do is we want to make sure that we don't have them, and since we know that we're not going to be able to have them, or that we're never going to be able to reach that point of perfection, what we then want to do is at least control the ones that we have. And since a lot of it is going to be coming out of the inside of this drive, it just makes sense that we are going to go and try and block it from getting out on the drive back onto the mains, as well as we're going to try and block it from getting out of the drive and getting onto the motor. Inside of the motor, we deal with more problems like reflected wave and windings that are going to go and fail. Inside of the rest of the system, we deal with other components that are either going to be overheating, they're going to be triggered off to high voltage, DVDT that can go and cause other issues to start as well. We'll use a bunch of different things to do this. Line reactors, isolation transformers, and harmonic filters are going to go and be common ones. Harmonic filters are just going to be series RLC circuits that are tuned to specific frequencies so that they've got the minimum amount of resistance at those specific frequencies. And then my other ones, my reactors, are just going to be smoothing. My transformers, isolation transformers, are great because it's two reactors basically that are going to be back to back that are going to go and give us doubly the amount of smoothing out of these things. On a high quality system, what this should go and look like is that you should have your VFDs, especially if it's a large motor. If it's small, like 1 or 2 horse, you're probably not going to see that much for your input. But if you're dealing with, a 40 horse or something like that, you want to make sure that thing's going to be isolated off your main lines. You're going to do that through the use of an isolation transformer on the incoming side, and then you're just going to pass through there throughout to the other side. You're going to stick reactors that are usually going to be in line with the motor. Reactors are just going to be inductive chokes that are going to be in line. They filter out a lot of our high frequencies and things like that. Looking at the drives themselves, over here we've got a very small little drive. I don't even recognize actually who that manufacturer is now that I take a look at it, but they're all pretty similar once you pull the covers off of them. Very common that when you go and pull the covers off, that the control, the operators interface over here is going to go and stay with it. This is very often going to be called the HMI, the Human Machine Interface. It's not a GUI. GUI is a software one, but HMI is a Human Machine Interface. And I see that it's made up of, it's got a function button, a stop, reset, a run, and then a 1 and a 2 that also have arrowheads associated with them. These are just going to be membrane switches that the operator is going to be able to go and poke, to go and adjust. They go through function to get into the menus. From inside the menus, they select which menu, and then they can go and, make adjustments as well as adjust motor frequency on the fly. When you go and pull this cover off, it is going to go and remove, in a lot of cases, the whole HMI directly off of there. Oftentimes the HMI is plugged directly in. Over here you see we've got a set of buses where that HMI will plug directly into. Other times it's going to be ribbon cable connected. And then we have got a whole set of terminals that are going to be down here at the bottom. Those terminals that are in the bottom are going to go and have all of our motors connections, as well as we are oftentimes going to go and have additional controls connections that are going to be made on them as well. By the way, for those of you that have never dealt with these motors before or with drives before, we commonly have U, V, and W that are going to be utilized to go and indicate that this is going to be my ABC on my load. And then coming in on my lines, I'm going to go and have L1, L2, L3 commonly, or sometimes they'll have an ABC, but it's pretty standard. That's going to be L1, L2, L3 on the incoming, UV, W, that's going to be on the outgoing. I have seen more VFDs destroyed off of people putting power into UVW and trying to take it off L1, L2, L3 than any other method that you as electricians are going to go and find to go and destroy these drives. And it's a simple issue. Just read the manual that came with it. If you get a VFD, that VFD is going to come in a box, and when you unpack the box, it's going to have a manual. You're going to go and flip through that manual until you find the associated drawing for these things. We also have got, in some cases on these things, that we're going to be able to plug these things onto a network, where we're going to have network communications that are going to be done either through serial, they could be done through Ethernet, at times they're even going to be done through coaxial, although those systems are pretty old and pretty much out of there. If I've got a bunch of drives to program as well, a lot of them go and carry their memory on, they're going to carry them on just these little memory cards. Sometimes they're SD cards that you can go and insert into these things to carry that memory through from one to the next. But other ones are going to go and have other types of non-volatile memory. But it'll be the same that if I've got, a whole pile of these that I'm going to go and put together for a ventilation system, what I'll be able to do with that is I can take these, I can program one of these, and then I can store it onto that card, and I can pull that card out, and then I can carry it to the next VFD, just drop it in, and it's save it to that one, then carry it out, take it to the next one, drop it in, save that one, etc. And so it allows you to really do a lot of programming relatively quickly, particularly if you're doing, built from scratch type of systems. If you're putting together systems for, pumps, and you're always shipping out the same system, you program them all the same, it's a really fast way of doing that. The motor, we've talked about a number of times as well, that the motor needs to be that inverter duty. This is the first place that the module even bothers to explain what that inverter duty is. Inverter duty is just going to go and be a motor that's going to have hardened windings, better quality insulation. It's able to withstand the reflected waveform. It is going to go and have slightly larger conductors inside of it per horsepower, because we have got more skin effect that we are going to have inside of those as well. VFD inverter motors are also going to go and have more robust windings in the way that they can dissipate heat. Because if we're operating a VFD, that means at times we're going to be below our rated speed, and therefore it's going to be running hot. We're not going to get our cooling. So they will go and have, better windings for that reason. Once again, if you're going to be running these things below rated FLA for extended periods of time, make sure that that motor is either able to do it or that you've got external cooling that is going to go on beyond it. Anytime that you do run a motor, by the way, underneath a reduced speed, remember that my VF, that VF curve, that, or not curve, was a line that had to go up. We kept those things the same. if I'm keeping my VF constant on my motor, I'm going to go and have a reduced amount of current. Still going to get torque out of that motor at that reduced value of voltage, but I'm going to go and have a reduced amount of current, which means that I do need to have those overloads programmed into there so that my motor understands and can be, or so that my VFD understands and can be responsive to it. The most important thing that you're going to do is you're going to select proper cables. When we started to play around with VFDs, we started to find all these other issues that, we had weird things happening to other computers around, radio signals, and you could tell, you'd turn the thing, the motor on, and all of a sudden the radio in the room would drop out and go fuzzy and things like that. When we started to, address these, we found out that a lot of it was just that we were getting massive amounts of induction caused by these cables. And there's two main things that happen. One is we induce harmonic currents into other systems. And the other one is that we're going to go and get crosstalk. Crosstalk is where frequency from one ends up on another cable because they're near enough. We usually do use the term crosstalk when we are dealing with our low voltage communications, like if we're looking at Ethernet or a telephone or something, but it happens inside of power as well. It's just going to be a smaller magnitude, but it doesn't matter that it's a smaller magnitude because it still exists on there. And once again, if I get high frequency crosstalk, it can trigger DVDT inside of some of my semiconductors. So what ended up happening is we found that, the ground system was going to be very critical. That sheathing or wrapping was very critical. You'd stick these things inside a conduit, the problems would disappear because the conduit would be acting like a Faraday cage. But conduit's not practical everywhere, so you'd be looking for something that you could use, you could run them in that's not conduit. Tech cable became very popular for a while. We also found out that symmetrical arrangement was going to go and be very necessary, where I'm going to go and take my grounding, or so it's my bonding conductor, I'm going to split it into 3 components and run them across here so that each one is going to go and get the exact same amount of frequency. Because when I only had a single bond conductor sitting right over here, it was effectively anything that the C phase over here had for flux was effectively going to be blocked by these other 2 conductors because they're going to have their fields at any given time as well. So instead of just having, this imbalance, and then as a result, that we're starting to go and develop voltages, we just split this bond across them. And then last of all, you want to keep these things short. The longer that you go and run these things, the more inductance that you are going to go and have, right? Remember, L is equal to N squared mu A all over top of little l, which is going to be my length. Even straight runs of wire have got inductance, and that inductance, when dealing with super high frequencies, leads to inductive reactance. And then that inductive reactance would mean that at times we would not be able to go and reach the load with our full rated amount of power. Altogether, all the experimentation in the field, what people were figuring out, and then what manufacturers were dealing with, are, we're finding from that, led to the development of what we refer to as priority 1 VFD cable. There is going to be other priorities, priority 2, 3, etc., but the most common one is going to be the priority 1. It's made up of these, where I'm going to have my 3 main phase conductors. They are actual conductors on the inside of these. That's just showing the insulation. 3 main phase conductors that are going to be twisted together. Then we are going to go and have our bonds that are going to be separated, placed around that. And then around the outside of that, we are then going to go and have our copper tape shield. This is just going to be filler cables. Those plasticky white strings that you see inside of cables, that's all that we have over there. And then around the outside of that, we had the insulation, the armor that we were going to go and have. That insulation, we did want it to be continuous. It doesn't work very well for you to just go and use BX. We want to go and have this thing insulated because the only place that our sheath, that's this section over here, should be making contact is going to be at the source once again. The bond carries all the way through. The bond, is going to be connected to if this is my VFD, and if this over here is going to be my motor, the bond inside the cable is going to go all the way through the cable, be connected to the motor, be connected over here. But the actual sheath itself is only going to be connected back at the source over here. That's why we have to have the plastic around it, because otherwise, if this thing is not encapsulated in plastic, the sheath over here, then it would be able to go and short out between that and any other bonded components. AWG size is also going to be larger. When you take a look at it, you're going to pick up a number 14 cable and you're going to be like, I don't know, this looks like it's a number 12. Use the number 12 slots on your wire strippers because it is actually going to be closer in size to a number 12 than anything else. Over here, they show just another picture showing one. Once again, you see that bonds split into 3. You see the individual phase conductors that we're going to have. We see that we have got that sheath that is going to be around here, that tape shield as it's referred to. And then PVC. Then this over here is just going to be armor. This isn't a flexible cable. This is just, well, it's flexible, but it's not designed to like be a portable power cable or anything like that. This is going to be armor for protection, not for anything to do with electrical isolation. It's simply there for mechanical protection. Okay, circuit connections. When you do make your circuit connections, what we said there before, that U, V, and W. U, V, and W are going to be your connections that are going to go all the way over to your actual motor itself. You're going to have your lines in that are going to go into the line 1, line 2, and line 3. Or if it's single phase, it's usually going to be line 1 and line 3 that you're going to have. When you are going to be laying these, there's a whole set of stuff that you should be reading inside of your binder over here, paragraphs of stuff. But the big thing is just separation, separation, separation. If you've got, Ethernet, keep it far away. If you've got any type of analog control, keep these far away. If you have got any other type of power wiring, keep these far away from any of that, as well as from other VFDs. The best thing that you can do is just run these things on their own. You'll have installations where you're going to have all the rest of the power wiring that's going to be run inside the cable tray, and then you're going to have this single, VFD cable that's going to be strapped along the wall, because it's the only place that you can do it where you're not going to go and cause interference. Startups, startup and adjustment, we have talked about that. There's not much new inside of here, other than that. Finally, the module once again says that super important thing, that make sure you're programming this thing to go and match what the motor nameplate itself is going to go and be. If you don't put in the nameplate data, the VFD does not know how to respond to overloads, as well as it does not know how to properly do its VF. Remember, these things can put out smaller than the rated voltage. 600 volt drive, I can actually go and get 300 volts. I can get 240 volts out of it. I can run a 240 volt motor off of it, provided that I go and tell the drive that I'm not going to be, running 600 volts. I'm just running 240 volts off of it. So it makes it really, really handy on some installations where you might have a 600 volt system, and then there is a piece of equipment that comes in as a 208 volt motor. It turns out you don't need to have an isolation transformer or anything like that. You're just going to go and take that VFD at 600 volts. Not every VFD can do this, by the way, but you are going to go and take 600 volts. You're going to program your motor nameplate data in there that this is a 240 volt delta motor, and then you're going to be able to put out no more than 240 volts. Once you program that, then the drive itself scales the VF. It just says, okay, so full frequency is going to be 60, and that means that instead of this being for full voltage at 600, this is now going to be 240, and so then it's still going to maintain that proper VF across it. Yeah, I don't have a lot more that I really want to talk about on the startup. On the maintenance of them, the only thing to watch for is going to be any sort of stored charge. These things do have huge capacitors inside of them. It doesn't matter whether we're CSI or whether we are VSI. They're both going to go and have caps that are going to be doing different things, but they're still going to be inside there to go and provide power or to go and filter. They're big caps, and they're going to go and take a good 5 minutes before they're going to be completely discharged. One of the worst things you can do is just shut off power to the VFD and go poking around there immediately, because you've still got a lot of voltage on the DC bus. And if you accidentally contact that DC bus, it's going to hurt. DC hurts way, way worse than AC ever will. All right, that is it for this learning task. Go out, hook these things up properly, buy the proper cable. Yes, it's expensive. Yes, your bosses are going to whine about why do we have to go and buy this, but it is the proper thing to do. You're not going to be coming back to installations where you're pulling a whole cable out because you got reflected wave on your cheap old piece of BX that you tried to put in or anything like that. And filter them. Just filter them, filter them, filter them. Once again, the point of the filtering, this filter over here is to protect the motor. Protect motor. And it's just to protect the motor from anything that's going to be happening inside of the drive itself. The purpose of this filter over here is to protect the rest of the system. Guaranteed, it is more critical to protect the rest of the system, your warehouse, your shop, whatever it is going to be, you want to protect the rest of the system from the garbage coming off of your VFD. So make sure that if you're not going to do anything heroic, then make sure at least you do, as a bare minimum, a little bit of filtering on the incoming side. A lot of drives, by the way, do have reactors, built-in reactors. If you're not sure what to do, if you don't want to have to spend hours trying to sort out what the proper size is, buy a VFD that has a built-in reactor. There's loads of them out there. The manufacturers put them in there because the manufacturer is sick of dealing with burnt-out VFDs and complaints about motor warranties. So they've started to build these things with the reactors as component. You can buy them separately without the reactors, or you can buy them with the reactors. When in doubt, filter it out. Okay, if you don't know that's going to be a problem, go and err on the side of that it might be a problem, and just make sure you get rid of it. All right, that covers off our motor drives. We're going to take a look at PQA next.